Hey everyone, welcome back to TechBit Academy. Please like this video and subscribe to the channel.
Welcome to this explainer. Today we're diving into the totally invisible but incredibly high-stakes world of software testing. We interact with software literally every single minute of our waking lives. We trust it with our bank accounts, our healthcare, our physical safety. But right behind those sleek interfaces we're swiping on every day, there's a ridiculously complex architecture of code. And when that code fails, well, the consequences can be absolutely staggering. Before we get into how developers actually protect their code, we've got to stop and ask ourselves a pretty serious question. Just how catastrophic can a single unchecked error truly be? And we're not talking about your phone freezing up or having to restart an app. No, we are talking about astronomical financial losses, all triggered by the tiniest of oversights. To put this into perspective, let's look at this number. $125 million. That is the exact amount of money completely wiped out back in 1999. And the crazy part? It wasn't some sophisticated cyber attack. It wasn't a massive hardware meltdown. It was literally lost because of one tiny coding mismatch in a single calculation function. Or check out this even larger figure. $370 million. Vaporized in seconds. This happened when a highly advanced rocket actually self-destructed midair. And the culprit behind it all? An untested piece of reused software. Basically, someone assumed old code would just work in a brand new machine, and that assumption cost over $1/3 billion. Now, if you think those disasters took a while to unfold, get a load of this number. $440 million. This absolute fortune was lost in just 45 minutes by a major trading group. It absolutely proves that missing a step in the testing process isn't just some annoying IT headache, it's a financial disaster just waiting to happen, literally at the speed of light. So you're probably wondering, how do things actually go this wrong? Let's start by zooming in on the absolute micro level of code. We're going to look at the infamous loss of the Mars Climate Orbiter in 1999. NASA sent this magnificent piece of engineering all the way to Mars, only for it to be completely lost in space. Why?
Well, the fatal mismatch was almost laughably simple. You had two different systems trying to talk to each other, but they were using completely conflicting units of measurement. One was calculating thrust in imperial units, and the other expected metric. It's kind of darkly ironic, right? Literal rocket scientists missed a basic, everyday conversion error, but that one simple mistake completely threw off the navigation on a $125 million interplanetary scale.
The antidote here is what developers call unit testing. Think of it as your very first line of defense. It basically involves taking these individual calculation functions and checking them in total isolation. For the Mars orbiter, if they had just run a simple unit test to check the specific input and output of that one thruster calculation, it would have caught the unit mismatch instantly.
So the really crucial takeaway here is that ensuring the smallest pieces work perfectly is the absolute foundation of preventing total failure. Unit testing makes sure every single function is structurally sound before you even think about connecting them together. Because, as we just saw, even a tiny mismatch in a single function can destroy an entire mission. Okay, zooming out from those isolated units to see how different parts interact with each other, we arrive at our second case study. The terrifying 1996 Ariane 5 rocket explosion. Now, this wasn't an issue with just one isolated function failing on its own. It was a massive issue of compatibility. Basically, the developers reused older software from the previous Ariane 4 rocket. And hey, it seemed like a smart, efficient shortcut, right? But they ended up cramming a massive 64-bit velocity number generated by the new rocket into a tiny 16-bit space that the old software expected. It's like trying to fit a gallon of water into a shot glass. The system just couldn't handle it, causing a complete chain reaction of failure that blew up $370 million right in the sky. And this right here is exactly why we need integration testing. Once your individual units pass their own tests, you have to verify that they actually play nicely together. Integration testing explicitly checks that when you plug module A into module B, they don't blow each other up. It's all about testing the handoffs, the communication, and the data flowing between the different parts of the system.
This brilliantly illustrates a really important rule. Just because code worked flawlessly in the past doesn't mean it's going to safely interact with a brand new system. The Ariane 4 code was perfectly fine for Ariane 4. But in Ariane 5, without integration testing to check that specific new connection, it was literally a ticking time bomb.
All right, let's zoom out even further to the whole machine and take a look at the terrifying 2012 collapse of Knight Capital Group. This is where things get incredibly fast and incredibly expensive. Remember, we are talking about $440 million lost in just 45 minutes.
What happened here was a massive deployment issue. A faulty deployment caused old, obsolete trading code that was supposed to be dead and buried, to suddenly wake up and activate. But the real kicker is it activated inconsistently across their live servers. So the system essentially went rogue, firing off erratic trades at a blistering pace because the overall environment was just completely out of sync.
The missing link here? System testing. This is a rigorous, absolutely mandatory phase that demands you test the entire setup end-to-end exactly as it would run in the real world. It's not just about the individual units anymore, and it's not just about modules communicating. It's about taking the entire software package, running it in a production-like environment, and seeing how the whole machine behaves under the exact conditions it's going to face when it goes live.
You can have perfect individual parts, and they might even integrate well in small batches. But if you don't test the complete machine before deployment, you are risking a Knight Capital-level disaster. You've got to ensure that the deployment process itself and the entire system architecture functions perfectly as one single, cohesive organism.
Finally, we zoom out to the ultimate macro level. This is the point where the code actually meets the unpredictable, messy, real world. And our case study for this is the infamous 2013 launch of healthcare.gov.
The site was built, the modules were connected, the system was deployed. But because the developers failed to run adequate beta tests with massive amounts of simulated users, the site immediately buckled and crashed the exact moment real human traffic hit the servers. They just weren't prepared for the sheer volume of actual citizens trying to log on all at once. This brings us to the final frontier, acceptance testing. This is the ultimate trial by fire. It's designed to prove that the system can actually handle the business requirements and the real, live humans it was built for. This involves beta testing with actual users to make sure the interface makes sense, and intense load testing to simulate heavy traffic so your servers don't literally melt on launch day.
Ultimately, flawless internal code means absolutely nothing if the system collapses the second the end user tries to log in. You can have the most beautifully written software in the entire world, but if it doesn't meet the user's requirements or survive real-world impact, the project is a total failure.
So, when we pull all of this together, we can really see how these four distinct levels, unit, integration, system, and acceptance, aren't just annoying independent chores. They form an interlocking, comprehensive defense strategy against catastrophic bugs. We've seen the real-world disasters, from the Mars orbiter all the way up to healthcare.gov, that happen when just one of these layers is neglected. By following this natural life cycle step by step, from testing a single isolated function all the way up to simulating massive user traffic, developers are casting a massive safety net. This layered approach ensures that every single vulnerability, whether it's big or small, is caught well before deployment. It's truly fascinating to think that the greatest software testing goes entirely unnoticed by the public. When an app just works, or a rocket successfully launches, or a complex trade goes through perfectly, it's a quiet victory of rigorous testing. It really leaves us to wonder, looking at the devices we rely on every single day, just how many billion-dollar disasters were quietly prevented by developers today. Thanks for joining me on this explainer, and keep questioning the code behind the curtain.